All right, so the last piece of information that I wanted to give you is the integration of even and odd functions. So sometimes, even with a change of variables, meaning a U substitution, variables, integrating can be very difficult. Sometimes you can simplify the evaluation of a definite integral over an integral that is symmetric about the y-axis. Or about the origin. When you recognize that the function is even or odd. This is again something that was introduced in pre-calculus, the idea of an even or an odd function. So the theorem goes as follows. And this is integration of even and odd functions. So the theorem says to let f be integrable on the closed interval negative a to a. Notice that this is symmetric. Then 1, if f is an even function, then the integral from minus a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. This can be very useful at times, especially when simplifying or dealing with a complicated problem. Let's see another one. So the other part of the theorem says that if f is an odd function, then the integral from minus a to a of f of x dx is equal to 0. So the most popular even and odd functions are sine and cosine. Also, another popular even and odd function will be, so if you look at a parabola will be an even function. If you look at a linear function, it will be odd. So this is an odd function, this is an even function. Okay, when you plug into an even function, negative x, it's going to be equal to positive x. This is an even function. For an odd function, f of negative x is going to be equal to negative f of x. This is an odd function, or negative x. You could look at it as negative x. So it'll be an odd function. Okay, so let's do one example of this. And this will certainly be the last example that we do in this class, aside from review. So let's evaluate the integral from negative pi over 2 to pi over 2 of sine cube of x times cosine of x plus sine of x times cosine of x dx. Okay, so this is actually a very long and tedious integral, but notice that this is symmetric because we're going from negative pi over 2 to pi over 2, so we're going from pi over 2 to pi over 2. So the origin will be your axis of symmetry. Now, if you let f of x be equal to this whole thing, if you let it to be equal to sine q of x times cosine of x plus sine of x times cosine of x, we have the following. We have that if you plug in negative x, what do we get? We get sine cube of minus x times cosine of minus x plus sine of minus x times cosine of minus x. And this is equal to, remember, sine is an cosine is an even function, sine is an odd function. That's something that you should know from pre-calc. So because sine is an odd function, by the rule that I wrote up here, we're going to have minus f of x when you plug in negative x. So instead of having sine cube of minus x, you're going to have minus sine cube of x. Cosine is an even function, so you're going to have cosine of x here. And again, sine is an odd function, so you're going to have minus sine of x. And cosine is even, so you're going to have cosine of x. But notice that this is simply equal to negative f of x. Because look at what f of x is. We just you just multiply by a negative 1 because you made this first expression negative and the second expression negative. So this is an odd function. F is an odd function by the definition of odd. You plug in negative x, you got negative f of x. So f is an odd function. Odd function. And since f is symmetric about the origin, which is what we spoke before we began the problem, over the integral negative pi over 2 to pi over 2, we can apply the theorem. And what did the theorem said? Notice how nice this is. The theorem said that if f is an odd function over a symmetric interval, then the integral is actually equal to 0. So by applying the theorem, we have that the antiderivative from pi over 2 to pi over 2 of sine cube of x times cosine of x plus sine of x times cosine of x dx is equal to 0 by the theorem. And this is one of those theorems that you don't get to use a lot, but it can come in handy if you know it. It can definitely come in handy. I hope that you learned something in this class. I definitely hope that you remember the fundamental theorem of calculus. It's the theorem that you should never forget in your life, much like you should never forget the second fundamental theorem of calculus, the mean value theorem, the squeeze theorem, the extreme value theorem. All of these are theorems that, you know, they will keep coming up the more math courses that you take. So you should definitely keep a note for all of those. The book for this class has the proof written for all of these theorems. And if you are planning to major in mathematics, I do suggest that you read them. You may not understand a thing that they say, but you should definitely read them. You should also read a little bit about the life of people like Riemann or Newton or Leibniz, the creators of the people who are attributed to creating calculus. This is certainly something that is useful in every aspect of life. Although you may not realize it, calculus is used in everything that you see around you. With that being said, I hope that you enjoy the semester, and I hope to see you soon. Thank you for your time, as always.